Today in this seminar. My name is Hans-Martin Heyn, and I'm a postdoctoral researcher at the Computer Science and Engineering Department of Gothenburg University. And I'm going to talk about setting AI in context, or why data for AI actually needs to know the context. I'm mostly working with a project called VETLIOT, and VETLIOT stands for Very Efficient Deep Learning in the Internet of Things. And the mission of this project is to design, develop, and demonstrate the next generation of cognitive IoT devices using heterogeneous distributed architecture, integrated accelerators, leveraging a toolchain based on artificial intelligence and deep learning, demonstrated at a wide range of use cases. Now, this is quite a mouthful of things that we want to do in this project, but basically it means we are trying to distribute deep learning not only on one local device, but on several devices that might be connected through the IoT. And this is actually a good example of a large-scale agile system development that we are trying to do here. And this is how this project is set up. And I'm not going to explain all the details of this very complicated graph here now, but what is important to know is that we have three applications or use cases in which we want to try our distributed deep learning. One is a smart home use case, one is an industrial IoT use case, and there especially fault detection on motors and on power grid. And one is an automotive AI application where we are designing a more intelligent automatic emergency braking system for autonomous driving. And we have several work packages working with the middleware, with accelerators, with the necessary hardware, with security and safety aspects. But we are also having, of course, a requirement work package that kind of glues everything together. I'm just using this laser point here. And I'm going to tell more about this requirement work package in VETLIOT. So in the next 20 minutes, we will talk about challenges when defining the context for a system with AI. We will see that data quality and information are actually two different aspects. We will discuss data quality attributes and a framework to manage them. And we will think about information content of data sets and how it affects the behavior of the AI. So let's start to talk about what is actually context. And the easiest way to find a definition for a term is to look it up in the dictionary. Let's look it up in the Advanced Learners Dictionary for the English language. And it defines the context as the situation in which something happens, and that helps you to understand it. And it also provides an example. For example, such databases are being used in a wide range of contexts. But maybe we need a little bit more detailed definition of what context is for a computer system. And in this paper from Chen et al., titled An Ontology for Context-Aware Pervasive Computing Environments, they define the context as the context is information about location, its environmental attributes such as noise level, light intensity, temperature and motion, and the people, devices, objects, and software agent it contains. Context may also include system capabilities. Now here we get a kind of really nice list of what kind of information should be contained in the context information. Location is named, environmental attributes are named, but also stakeholders of the system and the own system capabilities. Now, let's look at automatic driving, because automatic driving is actually a very context-sensitive system, and it needs to be aware of the context it's operating in. Why? Because the context governs rules for how the automatic driving is supposed to work. For example, the context country determines speed limit and other rules. And if you have ever crossed a border in the European Union, you're probably very familiar with these signs that await you directly after the border, telling you some information about the new context. And context in this sense is here the country in which you are going to move now. So for example, if you cross the border to Germany, it will tell you you can drive 50 kilometers per hour in the city, 100 kilometers per hour outside of cities, and the most famous, you can drive you are recommended to drive 130 kilometers per hour on motorways, but there is actually no speed limit on motorways. I'm sorry, there's someone in the call that has a speakers on. I'm hearing my own echo. Okay, I'm continuing. However, the context in Sweden is different. And here, look at when you're outside of a city, you're not allowed to drive 100 kilometers per hour. You're only allowed to drive 70 kilometers per hour. And motorways, of course, have a speed limit of 110. Plus, the sign also tells you in the context of Sweden, you actually have to put on your headlights every time, even during the day, when you are driving, unlike in Germany. But this sign also gives us some information about if we envision to design a system that can automatically recognize speed limits in a given country, it tells us some information about the data we actually need to provide such a system for training. Because did you notice that Swedish speed limit signs actually have orange backgrounds, unlike German speed limit signs that have white backgrounds? Or did you notice the different font of the numbers in the street signs? So imagine you have a system that you trained for recognizing speed limit signs on German roads. It will have been trained with data containing street signs, speed limit signs that have a white background. So you cannot really guarantee that it will also recognize speed limit signs with an orange background and with a different font for the numbers. And it gets even worse. Imagine you are now driving into the United States, then even the physical units of the speed limit change, because the signs, they don't tell you the unit. The unit you are assuming from the context in which you are seeing the sign. So in Sweden, we know that we use kilometers per hour as a speed unit, but in the United States, they're using miles per hour. Now, it is quite unlikely that you will use a car that is designed for Europe in the United States. But imagine you are living in Ireland, in the northern part of Ireland, and you are crossing the border that you are not actually seeing into Northern Ireland. Suddenly all the speed limits are not in kilometers per hour anymore, but in miles per hour, because in Great Britain they're using miles per hour as well. So of course, people thought about this problem, and the Society for Automotive Engineering, they actually came up with something they call an operational design domain, and they define it as follows. The ODD describes the operational condition under which a given system for driving automation or feature thereof is specifically designed to function, including but not limited to environmental, geographical, and time of day restrictions, and/or the requisite presence or absence of certain traffic or roadway characteristics. So would this solve our problem? We just define operational design domain. Let's say our system operates in Norway or in Germany. Let's take Germany. So now we have a use case that we have a user that would like to use an automatic driving system in the city of Aachen, which is in the very west of Germany. It's quite a beautiful city. Aachen is somehow special because it's surrounded by two countries, Belgium and the Netherlands. And some suburbs of Aachen, for example, the suburb of Kerkrade, it's very much divided between the Netherlands and Germany. And now envision you have a car or an automatic vehicle that can only drive in Germany because we limited the operational design domain to Germany. There is one street called the Neustraße or New Street in Kerkrade, and this street is quite special because the border goes exactly through the middle of that street, meaning the right-hand side of that street is in Germany and the left-hand side of that street is in the Netherlands. And so are the street signs. The street signs on the right-hand side of the streets are all German street signs. The ones on the left-hand side are all Dutch. So our vehicle that can automatically drive in the operational design domain of Germany, it can drive northwards on this street, but it will never be able to return, because to return, it would have to drive in the Netherlands, for which it hasn't been designed. A second example is a person who lives in Mo i Rana in Norway. He would like to drive his automatic car, but in Mo i Rana, Norway is very narrow, meaning there's not a lot of space for roads. And actually, there's only one single road that goes to the south from Mo i Rana, and that is the E6. And it happens once in a while that they need to do some maintenance work on that road. And then the only way to get south is actually to drive via Sweden. Now, if you have a car that you bought in Norway and that is only designed to work in Norway, and Norway has actually white backgrounds in the speed limit signs, then you will get a big problem because you will not be able, until the maintenance work of the E6 is done, to drive south automatically with your car, because your car is not designed to operate in Sweden. So what we learn here is limiting the operational design domain to fit the context might not fulfill all desired use cases, because you have these corner use cases where, yeah, obviously the person living in Aachen lives in Germany and buys a car in Germany, but he always wants to drive also in the Netherlands. Or this person living in Mo i Rana, he lives in Norway and buys a car in Norway, but still the car needs to be able to drive in Sweden. So the UDD can only be a subset of the context. And the problem is, how do we actually argue for completeness of the UDD? So a use case assumes a context, and the reciting requirements will only be valid in that assumed context. However, use cases are often quite general, and practitioners need to interpret how the context needs to be defined. The UDD guarantees the behavior of the system in a clearly specified domain, but does the operational domain cover the entire context of the use case? The problem is that there are no clear common processes or approaches on how to derive the context definition from use cases. Because, as I mentioned, the use cases are very general. The person in Aachen, he just wants to use his car in his everyday life. He doesn't care if the car is designed to operate in Germany explicitly or in the Netherlands. He just wants to be able to use it. And you as a developer have to make sure that this is fulfilled. So to actually figure out what a context definition is and what it should contain, we performed a case study at a tier 1 supplier for perception systems for driving automation. And we asked those 3 questions. What is the current understanding of context definition? What are the challenges with deriving context definitions from use cases? And which support would be appropriate for deriving context definition from use cases? And we did perform an interview study, meaning we prepared the interviews, we collected data through the interviews, we did a data analysis with external theme validation, and we also validated the results through a focus group. And we had one case company, we had 13 interviewees, and this included 5 interviewees from partner companies, OEMs, and authorities such as Trafikverket. And we used a maximum variation strategy, meaning the participants represented a wide variety of experiences and positions involved in the development of automated driving function, from a high top manager to a function developer. And I will not present all the results of this study, but I will provide at the end of the presentation a link to the full study. But I will give a brief overview of the results. There's a clear lack of standardization of concepts and processes for defining the operational context and deriving the UDD for automated driving systems. Because of the typically distributed development of systems in the automotive industry, this creates challenges which leads to misinterpretation and slow iteration loops between the stakeholders. And a major problem the study identifies are missing documentation of context assumptions. Whether a context is assumed or explicitly given through a use case can make a huge difference during the function development and testing. Furthermore, the study reveals a lack of involvement of function developers in the requirement engineering activities that lead to the context definition. And as a result, function developers often misinterpret or question the defined operational context. But we also asked the interviewees for possible solutions they could envision that could solve the problems. And there are obvious solutions, such as more standardization or deeper involvement of function developers in the definition of the operational context. But the participants also suggested ideas such as more diverse data about the context. Often it is hard to define the context because you just do not have enough data about the use case or enough information about what the use case entails and in which context it should operate. You need more completeness criteria for the UDD. You need to understand, okay, when do I actually cover the entire context with my design domain? And you need more efficient leveraging from other contexts. And what that means is that often you have a system that operates in one context and you would like to define it for or develop it for another context, then you could actually already use lessons learned from one context and move it to another context. And this is not happening too efficiently. And improved integration of context definition into scaled agile frameworks is lacking. So now I talked about context, and why did I do this? Because context is extremely important to actually understand what kind of data you need for your AI system. And here I will look especially at deep learning systems now as an example of machine learning. Machine learning and deep learning in particular depends on the data provided for training, validation, and doing inference at runtime, because it is the data that you use during training and validation that will in the end define the desired behavior or the behavior of your deep learning system or deep learning network. These networks, they create models of reality, and those models cannot be valid in all of the contexts because we cannot define a world model. We can only develop a model that is an abstraction of reality, but we need to know in which context this abstraction is actually valid. And the context for which the model shall be valid determines which data is actually needed. And there are two problems that arise here. There are only few methods to determine and manage the required data quality attributes. And the second problem is there's basically no method to systematically determine which information the data actually should contain based on the use case and the context. So I will start talking about the data quality attributes for deep learning. We need to understand the data quality needs for a desired behavior in a given context. And we need to develop a set of artifact components that try to address the data quality challenges. And we need to understand what kind of requirements should data have to be of quality. And we performed here a design science study with the following two questions. For the development of systems based on deep learning, what are the relevant challenges of managing data quality, and what constitutes a data quality artifact? As I said, we performed a design science study which contains 3 steps. We did a problem identification using literature review, interviews, thematic coding, and a survey. We developed a solution or a proposal for the solution design, again, using literature review, brainstorming with a partner company, and interviews. And we evaluated the solution using a focus group and survey. So first, we identified what challenges in data quality attributes actually exist, or in defining data quality attributes for deep learning actually exist. And we separated them into different challenge sets. Those are data availability challenges, data management challenges, data source challenges, data structure challenges, and data trust challenges. And I will not go through the entire list of challenges now. Again, they will be, you can find them later after the presentation in a link that I will provide. But altogether, we identified 27 challenges together with a partner company. It was, again, this tier 1 supplier company for perception systems for automated driving. And if you look at the list of challenges, some are written in bold, some are written in italic, and some are written in normal font. And this has a meaning. The bold ones we could find only through the interview data with participants from this tier 1 supplier company. The italic challenges were found only in literature, and the ones that are written in normal were found both in literature and through the interviews. And based on these challenges, we actually derived or proposed a framework that could be used to manage data quality for deep learning. And this framework contains 6 steps. We identify the data quality challenges. This is what we just did. Collect and organize data quality attributes. Determine data quality challenges that affect the data quality attributes. Define data quality attribute metrics. Identify solutions for data quality challenges. And of course, present and send them to the stakeholders. And I will now show the list of possible data quality attributes that we found for automated driving system. A set of data quality attributes. Collect and organize data quality attributes, meaning like what data quality attributes actually exist, what data quality attributes are relevant for our use case in the given context. And altogether, we found 82 different data quality attributes for automated driving. Doesn't mean that we need to always consider all 82 data quality attributes for each of the use cases, but we just provide them as an example of how many exist. And an artifact that we propose that could be used in companies to manage data quality attributes are actually these fields or these tables for data quality attributes. And these tables, they include fields such as name, reference, definition, and challenge that affecting the data quality attribute, metrics, and formula. Here's an example for timeliness given on these references, a definition, length of time between data availability and the event or phenomenon the data describes, and the challenges this is affecting this data quality attribute, such as data delay, data drop, manual data collection, and manual data label, and a metric. This is only one example out of the 82 examples that we found. But then you also need to find a solution for the data quality challenge, such as timeliness. And then again, we propose an artifact that contains the following fields: name, challenge it tries to solve, requirement specification, and implementation details. The example here is corroboration of data with central repository. And the problem challenge it tries to solve is data depending on an external condition. And the requirement specification could be define the central data repository, its structure and address, define the procedure if central data repository cannot be contracted, and define the way the AI disengagement is notified to the user. So the question then are, what challenge does it solve? What requirements do we need to include? And can we implement it? And as an example, we have 13 solutions that we propose in this study. So this would look, now we looked at the data quality attributes, but this only looks at the quality of the data. That would mean like what how the data is or how information is presented to a system. But actually we also need to look at what information the data should entail based on the use case and context. And for that, we propose that we develop some form of information model, and that work just recently started. So I do not have any clear results yet. I can only propose you the idea. So what we need is, based on the use case that we have for our machine learning system or any system that uses AI, and based on the context in which we want to use it, we need to develop an information model. And based on this information model, we can determine required statistical properties of data that need to be collected, e.g., for example, through experiment, or for example, through driving campaigns for collecting data on the road. And then we collect this data, and this data will have certain statistical properties that we can use to train our deep learning model, for example, with. But this information model will also provide us with ideas or with rules of what the data or what statistical properties the data should follow. And this will allow us to define data monitors that we can later use to validate that our statistical model is actually exactly following the information model that we would like it to do. So in conclusion, defining the context in which the use case, a desired behavior is valid, is not a well-established process, but the behavior of system with AI depends significantly on data, and that data needs to be valid in this given defined context. And we can differentiate between data quality attributes and information content of the data. So giving a use case in a given context, we can define data quality attributes that we need to follow, but we also need to define the information content that the data needs to contain. The context information is needed to define the required attributes, properties of the data. Simply feeding AI with data will not lead to the desired behavior. One needs to define requirements on the datasets used for training and validation of machine learning models. And here's a list of additional literature that you can use to get especially more of the results of our 2 studies that we already performed. And this finalizes the presentation that I wanted to give you today. Thank you very much, and I'm very happy to answer questions now.